Hi, I'm Rakshita from CSC AML sections. My topic is connecting the dots, identifying network structure via graph signal processing. Introduction to graph signal processing, GSP. Graph signal processing extends classical signal processing to data defined or irregular domains represented by graphs. A graph signal is a function mapping each node in a graph to a scalar or vector value, analogous to time domain signals in traditional DSP. GSP enables spectral analysis of data on networks using graph Fourier transform based on the graph Laplacian eigenvectors. Applications include sensor networks, social network analysis, brain connectivity, and recommendation systems. The core idea is to leverage graph topology to extract meaningful patterns from structured data. Graph representation and mathematical foundation. A graph G equals to VE consists of a vertex set V and edge set E with adjacency matrix A where Aij equals to 1. If nodes I and J are connected, the degree matrix D is diagonal with Dii equals to sigma j A ij, presenting the number of connections per node. The graph Laplacian L equals to D minus A captures the difference between a node's signal value and its neighbor's average. Normalized Laplacian L sin equals to t power minus 1 by 2 L t power minus 1 by 2. Induced scale invariance and is used in spectral clustering. Eigen decomposition of L yields eigenvalues lambda k and eigenvectors uk, forming the basis for graph Fourier analysis. Graph Fourier transform GFT. The graph Fourier transform of a signal x belongs to R power n is defined as x equals to u to the u power t x, where u is the matrix of Laplacian eigenvectors. Each eigenvector uk corresponds to a frequency mode with smaller eigenvalues representing smoother low frequency signals. High frequency components correspond to eigenvectors with large eigenvectors, indicating rapid signal variations across edges. In inverse GFT reconstructs the signal as x equals to u x, enabling spectral filtering on graphs. GFT generalizes the classical DFT by replacing sinusoidal basis functions with graph Laplacian eigenvectors. Spectral properties and signal smoothness. Signal smoothness on a graph is quantified by the quadratic form x power t Lx equals to 1 by 2 sigma ij aij of aixj power 2. A smaller xt Lx indicates the signal varies slowly across connected nodes, implying low frequency content. Smooth signals align with low frequency eigenvectors, enabling compression and denoising via spectral truncation. This metric is critical for defining band limited signals and designing graph filters. Graph filtering and convolution. Graph convolution is defined as y equals to u power t x, where G is a diagonal matrix of filter coefficient in the spectral domain. Polynomial filters y equals to sigma k equals to 0 power k alpha K, LK, X. Approximate spectral filters with localized support. Reducing computational cost. Graph filters can perform low pass, high pass, and band pass operations to extract structural features. Localized filtering allows node specific processing while preserving global topologic consistency. Network structure discovery via spectral culture. Nodes are clustered in these embedding using k-means, revealing community structure based on connectivity patterns. The eigengap selects the number of clusters by identifying large gaps in the eigenvalue spectrum. This method effectively identifies modular structures in social, biological, and communication networks. In semi-supervised learning, this propagates labels from labeled to unlabeled nodes based on connectivity. The regularized loss function becomes min f y minus f power 2 plus y ft lf. Balancing fidelity and smoothness. It is widely used in node classification, regression, and anomaly detection tasks. Graph autoencoders for structure learning. The encoders uses graph convolutional layers to generate node embedding z equals to f of xa. The decoders computes reconstructed adjacency a equals to sigma z z into t, where sigma is a sigmoid function. GAES can identify hidden communities, predict missing links, and detect anomalous edges. Random walk Laplacian LRW equals to d power minus 1 L. Models transition probabilities between nodes. The diffusion kernel expense minus beta L captures multi-hop influence and long-range dependencies. Personalized range rank uses I minus alpha p power minus 1 R to identify nodes influential to a seed vector R. This process underlies algorithms like label propagation and graph-based semi-supervised learning. Each layer aggregates neighbor features and updates node representations iteratively. Graph SAGE samples fixed size neighborhoods to handle large scale graphs efficiently. Attention mechanisms. Example GAT. Weight neighbor contributions dynamically using learned attention scores. GNNS. Learn both node features and graph structure, enabling end-to-end structure identification. Normal node exhibit smooth signals and energy concentration in low frequency components. Anomalous nodes show high energy in high frequency bands, indicating irregular connectivity. This method is effective in detecting bots, fraud, and faulty sensors in networked systems. Applications in AIML from theory of brackets. GSP enables interpretable AI by linking model decisions to graph topology and spectral features. In recommendation systems, user item graphs are analyzed to identify latent reference structures. Brain network analysis uses GSP to detect functional connectivity patterns in fMRI data. Autonomous systems leverage GSP for sensor fusion and spatial reasoning in dynamic environments. These applications demonstrate the engineering value of GSP in real-world AI/ML systems. Challenges and future directions. Scalability remains a challenge for decomposition based methods on large-scale graphs. Dynamic graphs require online algorithms for incremental Laplacian updates and spectral tracking. Heterophily connected nodes with dissimilar features limits performance of smoothness-based models. Future work includes quantum graph signal processing and GSP for hypergraphs and simplicial complexes. Thank you.